Hello and welcome back to part 3 of this video series on 3D printing. In this part we'll be completing our model. I had printed the design that we've talked about in the earlier parts and was starting to assemble the final product, as you can see in the illustration on the right. However, I soon realised that I had not allowed enough space around the pulleys, both for fitting the drive belts and also for allowing for the thickness of the pulleys. The other problem I had was that the motor required 2 pulleys on the end shaft, one for each direction, and the belts had to leave these pulleys perpendicular to the shaft, otherwise they wouldn't stay on the pulleys correctly. Therefore I had to move the motor outwards in order to fit both in between the back-to-backs of the wheels on the Simplex. This made it too wide and the motor would protrude through the wheels, and this wasn't something I wanted. It would be too visible. Therefore I decided I would look for another way of motorizing the Simplex. So this new approach I used took advantage of a small motor that I already had, another 6mm diameter motor, only this time it has a planetary gearbox attached to it, which gives quite a high reduction ratio. I also found a spur gear and a crown gear which would mesh together, and spur gear fitting nicely on the end of the motor, and the crown gear fitting on the 2mm axle of the wheel set of the Simplex. I decided I would therefore try and make a design based on using this motor instead of using the pulleys. It did have one disadvantage in that it would give me 2-wheel drive. This motor is quite long and there wasn't enough space to fit 2 of them underneath the chassis of the Simplex. So I went back to the drawing board. Well, actually no, I didn't go completely back to the drawing board. What I did was I took my existing design, the one that was using pulleys, and I used the feature of Fusion that allows you to remove material from a design to get rid of that portion I no longer needed. So what I did was draw a rectangle around the center section, which previously held the motor mount and the 2 mounts for the bearings that were used by the intermediate axles. Finished that sketch and then extruded it straight through with a cut operation to remove that material, and I was left with the basic frame, so the base and the uprights that would be supporting the axles. Of course, when it's turned the right way up, the base would be the top and the uprights would be the supports going downwards where the axles get mounted. What I needed to do was to create an angled mount for the motor. Now, the reason for this was the motor was too long to fit between the axles, therefore it had to be angled so that it went underneath the non-driven axle, but would still mesh correctly with the driven axle. It's very important with these gears that the motor shaft is perpendicular to the axle it's driving, and that if you take a line through the center of the motor, it passes through the center of the axle. That way the crown gear and the spur gear will correctly mesh. So this was a crucial dimension and angle required in this design. So the question was, how was I going to get this right? The motor alignment was actually not that difficult to do in the end, but took advantage of the features of Fusion. And I'm going to briefly show you how I did this by using the facility of Fusion to go back along its timeline and show the steps that were done to create the design. What I did was I drew a line from the center of the axle, that's the driven axle, back under the non-driven axle, and the length of this line being the length of the motor with allowance for the crown gear and the spur gear. I then drew this line at 4mm that was perpendicular to the line that came through the center. I drew another one at the rear and created a rectangle. Underneath this line I then created a trapezium. The reason for the 4mm dimension was because I had a 3mm radius motor, i.e. 6mm diameter. I finished that and then extruded it so that I had a block in the center. The front face of that block is now at the right angles to the direction I want the motor to be in. So I drew a line 4mm down to find the centre of the motor, and then a circle of 6mm diameter. When I then extruded that through the block, I had a hole in that block that was at the right angle to take the motor and would allow the gears to mesh correctly. I also added a few other features like these little side pods you see here with some holes in them to allow wires to pass from one side of the motor to the other, and also to house some pickups. This gave me a very accurate angle for my motor, and would hopefully mean that everything would mesh correctly when I started to assemble the chassis. So my next step, after having printed this new design, was to add the bearings, which were used for the wheel sets, insert the motor, and add the crown gear. You can see I've cut down slightly the spur gear because it was very long and meant that the motor would have protruded too far to the rear, so it was easy enough to just chop that down a little bit. So I then did an initial test run with a 9-volt battery, and as you can see the gears are meshed very well and the wheels are turning. The non-driven set here are rotating just through the vibration rather than anything else. They're not actually driven at all. So then the next step was really to add the pickups and decoder and to see how it would run. One thing with this setup is the motor was actually a 3-volt motor and the battery was a 9-volt battery, so it was actually driven much faster than it should be and was quite noisy as a result. But I had a way around this, as we'll see later. And now we get to put all the bits together and do the first test run of our Simplex. I fitted the pickups. These run in brass tubes that go through the holes in those side pods that we saw earlier. Inside these thin brass tubes is some beryllium wire which actually acts upon the wheels themselves. I've also fitted the DCC decoder, and this fits in a pocket that will be above the gear set. This pocket was specially made to fit a particular decoder. The wires from the decoder to the pickups can be seen here where they're soldered onto the brass tubes that go through those holes, and the wires to the motor go through the other holes in these side pods and connect to the far end of the motor. I've also added some weight. As you can see in this picture over here, there's some lead I put in the end here and also on this end here. I've also put in a representation of a white metal driver. I couldn't find a white metal driver at the time that was seated, so I've used this standing figure as a stand-in for this test. And I think I might need to add some more weight, but as you can see, it does run, and runs fairly well, quite slowly and smoothly. I've used CV57 of this decoder, it's actually a Z-mode decoder, to set the reference voltage of the motor down to 3 volts. This has helped considerably with the screaming noise that we heard when we did the initial test run with the 9-volt battery, and also with the top speed, so it now runs much more slowly and in a much more controllable way. You can also note there is not very much of the 3D printed chassis that's actually visible underneath it here. You can just see a small amount where the motor mount goes. But all in all, I was fairly happy with this test run. I think I'll still add some more weight, possibly replacing these buffers with some brass turned ones, and maybe a few other bits and pieces with some heavier detail parts. So what were the advantages and disadvantages of choosing 3D printing for this project, and was it a good thing to do? One real advantage of 3D printing is the rapid prototyping. Pretty much as fast as you can draw something, you can get the printer to print it. It takes maybe half an hour to print one of these chassis, slightly less I think. But it's fairly quick, and it's a lot quicker certainly than it would be if I was trying to make this out of etched brass, for instance, where I have to send away to etchers, or trying to scratch build it. Also means you can do incremental improvements. I obviously did one big change when I moved from the pulley system to the planetary gearbox system, in that I took out the whole centre and replaced it completely, but along the way I've done other incremental changes, such as adding reinforcings, adding these side pods, extending things, putting in the holes for the pickups, etc. And all of those things can be very easily done, and it's then just a case of printing another one and you've got what you need. Whereas if you had scratch built it, you would probably have to start again to do some of these things because they wouldn't be easy to add on. The other big advantage is the precision you get. I ended up with a square chassis very quickly because of the way that I drew it in the CAD package. It guaranteed things were going to be square, and when I printed it they stayed square. Likewise, the angle of the motor to get that gear meshing correct was fairly easily done using the CAD package, but it would have probably taken some trial and error if I'd done it in more traditional methods. There are some disadvantages. The plastic isn't heavy, so there's not much weight on the chassis, hence I need to add as much extra weight as I can. And there is some space even underneath to add a bit more weight still, as you can see from this picture here on the right hand side. The other thing is rigidity. It is a plastic chassis, so it's not maybe as rigid as you'd be able to make a metal one. Although because I've used a fairly hard plastic, in this case PLA, it has produced something that is reasonably rigid and doesn't move around very much, especially once it's actually in the body. The plate that the chassis is built on is quite thin, and that isn't as rigid as perhaps it could be. But as I say, once it's attached to the body, that's not a problem any longer. All in all, I suspect by using 3D printing, I've produced something more quickly and more neatly than I probably would have managed if I'd been scratch building this out of brass section, for example. Well, thank you for your interest, and hopefully this has given some insight into what's possible using 3D printing. By no means is this sort of project the only thing that you can undertake, but it's certainly something that is quite feasibly done with a home FDM printer. There are lots of other things that can be done, and that's very much up to your imagination. Once again, thank you for watching, and I hope you enjoyed it.